Section 4.3 is on complements, conditional probability, and Bayes' theorem. When it comes to the probabilities, we have this at least one probability, and this is where that's equivalent to one or more. So as a variable, that'll be x is greater than or equal to 1. The complement of at least 1 is less than 1. So x less than 1, which is basically the same thing as saying no occurrences of the event. So x is equal to 0, since you can't have a negative type of event in that case. For example, not getting at least one goal in 10 births means getting no goals, which is the same thing as getting 10 boys. You can't have negative goals in that case. The procedure for this is to first let A denote the event of getting at least one of some event, then A complement would be getting none of the event being considered. The probability of A complement would be the probability that event A does not occur, and it's usually calculated with the multiplication rule. Then we would subtract the result from 1. So, in other words, this is probability at least one occurrence of event A is equal to 1 minus the probability of no occurrences of event A. So, for example, when it comes to these at least probabilities, let's say the probability of randomly selecting someone with group AB blood is 0.0526. A researcher needs at least one subject having group AB blood. If 20 subjects are randomly selected, find the probability of getting at least one with group AB blood. Is the probability high enough so that the researcher can be reasonably sure of getting someone with group AB blood? So for this, we need to denote our event A being at least one of the 20 subjects has group AB blood. A complement then is less than 1, so none of the 20 subjects have group AB blood, which then that means that all 20 do not have AB blood. And in order for us to do this, we need to calculate the probability of at least one person having that group AB blood. It's the same thing as 1 minus the probability of none of the people in the group that are having AB blood. We were told that the probability with AB blood is 0.0526. So 526 10,000ths. But in order for us to do that, we would need the probability of one person, in this case, not having AB blood. That would be the same thing as 1 minus the probability of having AB blood. So 1 minus 0.0526, that's 0.9474. So for the none having the AB blood, again there's 20 people, we're doing 1 minus 0.9474 raised to the 20th power. Tossing this into a calculator gives us an answer of 0.661. So 661 thousandths. And the interpretation of that would then be that, yes, the researcher should be reasonably sure of getting someone with group AB blood, since that probability is greater than 60%. The conditional probability, which is based off of that multiplication rule that we have seen in a previous lesson, it's a probability obtained with the additional information that some other event has occurred. So it's denoted by probability of B given A. Alright? Or in other words, the conditional probability of event B occurring given that event A has already occurred. This assumes that event A has occurred and then calculating the probability that event B occurs after that. So the probability of B given A can be found by dividing the probability of events A and B, both occurring, by the probability of event A. So probability of B given A is equal to probability of A and B divided by probability of A, which basically is just a reworking of that multiplication formula by moving the probability of A over. So an example using the conditional probability is this. Based upon this table down here, if one of the 555 test subjects is randomly selected, find the probability that the subject had a positive test result, given that the subject actually uses drugs. We have 45 that it has a positive test result and uses drugs. So 45 in the numerator. The denominator being the probability of doing drugs. This would be 45 plus 5. The denominator is 50. So 45 out of 50, that's 0.9. If one of the 555 test subjects is randomly selected, find the probability that the subject actually uses drugs, given that he or she has a positive test result. The numerator is the same thing at 45 because despite the fact that we just switched the order of these two, it's still the same thing. The denominator now is the probability of being positive. So 45 plus 25 is 70, and 45 divided by 70 is 0.643. So that reduces the probability in that case. And as that last example does indeed show, you cannot interchange the order of these. So probability of B given A is not the same thing as probability of A given B. And because of that, we can't really switch on the formula. Bayes' theorem allows us to use applications that allow for revising a probability value based on additional information that is there obtained. And the actual formula itself is this lovely gem. Probability of A given B is equal to probability of A times probability of B given A divided by probability of A times probability of B given A plus probability of A complement times the probability of B given A complement. And this can be used with sequential events. It utilizes the prior probability, so initial probability value originally obtained before any additional information is obtained, and the posterior probability, that's the probability value that has been revised by using additional information that is later obtained. An example then of Bayes' theorem would be assume that cancer has a 1% prevalence rate. Denoting the event of having cancer by C, we have probability of having cancer being 0.01 for a subject randomly selected from the population. And this is based on this table down here. So from this we know there's a 1% prevalence rate of cancer, false positive rate is 10%, and true positive rate is 80%. We must find the probability of having cancer given a positive test result. So, number one, we could take the complement of having cancer, so not having cancer is 1 minus 1/100th, which is equal to 99 hundredths, or 0.99. So to find this formula, we take the probability of having cancer times the probability of having a positive result given that the person has cancer, divided by probability of cancer times the probability of having a positive result given that the person has cancer, plus the probability of the person not having cancer times the probability of getting a positive result given that the person does not have cancer. So for the probability of cancer, that's 0.01 times the probability of getting a positive result given cancer is 80%, which we could determine down here. We could also find it based upon on here as well, since we had 8 that had cancer out of a total of 10, so 0.8. Divided by 0.01 times 0.8 again, plus the probability of not having cancer we just said before is 0.99, times the probability of being positive given not having cancer. For this, that will be this 99 divided by the total 990, which is 0.10. and tossing this entire calculation into a calculator, we get a probability of 0.0748. Thank you.